Hello everyone, this is a run through the waves questions which are part of the Year 1 A-Level Physics workbook. So the suggestion is that you've got the workbook, printed out a copy of it, and that you've had a go at the waves questions under timed exam conditions, so that this run through is of most benefit to you. You can then check how you did, and you can get some help with the questions that you found trickier, and you can see what was needed for those questions, and in that way you can improve your capability to answer exam questions on this topic. So dive straight in to question 1. So which of the following is correct for a stationary wave? The answer is D. Between two nodes, all parts of the wave vibrate in phase. So it can't be A, because the amplitude actually varies between the nodes. So actually at the nodes it's zero amplitude, and the amplitude gradually increases as you work towards the antinode, which is maximum amplitude, and then decreases again as you go towards the node. So it can't be A. And B, two waves producing the stationary wave must always be 180 degrees out of phase. Well, they will be if it's a reflection of, let's say, a string at a fixed point where it's tied or fixed. But if it's a string which is loosely tied, or if it's an open-ended tube and you've got air vibrating, then they may not be 180 degrees out of phase. They might actually be a reflection at the point where they're in phase. C, it can't be C, because the second harmonic is high frequency, and therefore the wavelength will be shorter, and therefore the separation of the nodes will be closer together. It's not double. Okay, so that's a bit of explanation of why it can't be the others, and it's always good to go through that process. Question 2. So sound waves cross a boundary between two media, X and Y. The frequency of the waves in X is 400 Hz. The speed of the waves in X is 330 meters per second, and the speed of the waves in Y is 1320 meters per second. What are the correct frequency and wavelength in Y? So we know that the frequency will be unchanged as the wave crosses the boundary. That's one thing that will stay constant, and the frequency is determined by the source of the wave and doesn't change as the wave moves between media. So it's either B or C, because they show a constant frequency. And then we use F times lambda, that's the wave equation, to find the wavelength. So frequency times wavelength equals 1320. So which one of these two, B or C, gives us 1320? 400 times 3.3 meters equals 1320. So it must be answer C. Question 3. There's also multiple choice. The diagram shows two pulses on a string travelling towards each other. Which of the following diagrams shows the shape of the string when the wave pulses have passed through each other? So essentially it's got to be C, because well, the waves pass through and then continue unaffected. And that's the thing to realise about waves passing through each other. There will be a point where they overlap, and at that point you'll get interference. And so you could get A would be correct if it was at the point where they were crossing. But then once they pass through each other, they'll continue with the same waveform as they had before, just moving apart. So it's got to be answer C. Question 4 is a refraction question. So figure 1 shows a ray of light A, incident at an angle of 60 degrees to the surface of oil that is floating on water. So we've got some air, we've got some oil, and we've got some water and some glass. Given the refractive index of oil and the refractive index of water. So A part 1, calculate the the angle of refraction theta in figure 1. So we're looking to find this angle theta, given that the angle of incidence is 60 degrees. So we're going to use the Snell's law. N1 sine theta 1 equals N2 sine theta 2. N1 is the refractive index of air, which is 1. Sine theta 1 we're given as 60, so we're given theta as 60 degrees, so sine of 60 is equal to 1.47, which is N2, that's the refractive index of the oil, multiplied by sine theta 2, we're trying to find theta 2. So rearrange, sine theta 2 equals sine 60 over 1.47, and then inverse sine of that value gives us 36.1 degrees. And that looks about right, because we know that theta would be, the angle of refraction would be less than 60 degrees. Part 2, calculate the critical angle for the ray of light travelling from oil to water. The critical angle is the angle at which this incident ray, the minimum angle at which that can be set, so that all of the light is reflected. So at the point where the ray of light is reflected along the boundary here, which gives us an angle of refraction of 90 degrees. So we can use the same equation, but this time we're going to put in sine 90 for our refraction angle, which equals 1. And we can then, and then for the sine theta on this side, we're going to call that theta c, which is the critical angle. So that then simplifies to sine theta c equals N2 over N1. So it's the ratio of the two refractive indices. So we've got 1.33 for water and 1.47 for oil. And that equals 0.90476. Inverse sine gives us 64.8 degrees. So mark for substitution of the values correctly and mark for the final value. Part 3. On figure 1, continue the path of the ray of light A immediately after it strikes the boundary between the oil and the water. The angle of incidence is 60 degrees, which is less than the critical angle. So the ray is going to refract, and the angle of refraction is going to be less than the angle of incidence. So we're going to just draw that on. We're going to show an angle of refraction which is greater than the angle of incidence here. So this is 60, then this angle theta r is going to be greater than that. So it shows that it's refracting away from the normal. So in figure B, in figure 2, a student has incorrectly drawn a ray of light B entering the glass and then entering the water before totally internally reflecting from the water-oil boundary. The refractive index of the glass is 1.52 and the critical angle for the glass-water boundary is about 60 degrees. Give 2 reasons why the ray of light B would not behave in this way. Explain your answer. So reason 1, at the glass-water boundary, so we're looking at this boundary here, the angle of refraction should be greater than the angle of incidence. So it's coming in at an angle of 40, it's going to be refracting at an angle which is greater than 40. This is entering a less dense medium, or a medium with a lower refractive index. They've drawn it as refracting, bending towards the normal, it should bend away. And that's because the refractive index of water is less than the refractive index of glass. And reason 2, total internal reflection cannot happen at the water-oil boundary. So if we look at the water-oil boundary here, they've shown this ray of light totally internally reflecting. Basically it's reflecting back off that boundary. That cannot happen. Total internal reflection is only possible at a high n to low n boundary. So where the refractive index goes from high to low, a lower value. And this is a low n to high n boundary. So you can see the mark is, you've got marks here for the reason and for the explanation in both, so that gives a total of 4 marks. Question 5. An optical fibre consists of a core, cladding and an outer sheath. State the purpose for the outer sheath in an optical fibre. So it's for protection or to strengthen, prevents crosstalk, you could say, or interference. Part B. For one fibre, the speed of monochromatic light in the core is 1.97 times 10 to the 8 meters per second, and the speed in the cladding is 2.03 times 10 to the 8 meters per second. Calculate the critical angle for this light at the interface between the core and the cladding. We can use n equals c over v, so n is the refractive index. That's equal to the speed of light in a vacuum, the speed of light in the material, 1 divided by the speed of light in material 2. So 2.03 times 10 to the 8 divided by 1.97 times 10 to the 8 equals 1.03. That's a ratio, so there's no units. And then sine c equals 1 over n, which is 1 over 1.03, and inverse sine that, we get 76 degrees. So 1 mark for calculating the refractive index of that boundary by taking the ratio of the speeds, and the other mark is for calculating critical angle C using the relationship sine C equals 1 over n. I'm forgetting the final value correct. Okay, so musical concert pitch has a frequency of 440 Hz. A correctly tuned A string on a guitar has a first harmonic, which is the fundamental frequency, 2 octaves below concert pitch. Determine the first harmonic of the correctly tuned A string. So if you're going 1 octave below, we know the frequency halves, and if you're going 2 octaves below, it halves again. So it's going to be quarter times the concert pitch frequency. So that's going to be a quarter of 440, which is 110 Hz. Part B, describe how a note of frequency 440 Hz can be produced using the correctly tuned A string of a guitar. So you'd make the string quarter length. So if the wavelength is a quarter, then the frequency will be 4 times as big from the wave equation. We know that the speed of sound is constant in air, that the frequency and the wavelength are inversely proportional. The way you do that is to hold your finger on the fret to make the string quarter the length, but you don't really need that detail. It's just saying the string will be quarter of the length. 6C. Describe the effect heard when notes of frequency 440 and 430 Hz of similar amplitude are sounded together. So you would hear a beat frequency, and that's the difference between F2 and F1. F2 minus F1 in this case is 10 Hz. And a regular rising and falling of the amplitude, louder and quieter repeatedly. So the beat frequency, 1 mark, frequency difference F2 minus F1 would be an alternative to saying beat frequency. And in this case 10 Hz, that could be a mark as well. And then the regular rising and falling of amplitude, louder to quieter, would be a mark. So there's 2 max, 4 possibilities. Okay, question 7 is a Young's double slit experiment performed with a tungsten filament lamp as the light source. On the axis in the diagram above, sketch a graph to show how the intensity varies with position for a monochromatic light source. So I drew these with a graphics tablet. It's quite difficult to draw these well, but essentially you need rounded peaks, not triangular. Amplitudes are either the same as you move away from the centre or decreasing in amplitude. You would see a decrease in amplitude actually, but if you've drawn the same amplitude, that's okay, certainly not increasing as you go from the centre outwards. And uniform width peaks. So these are what the marks are awarded for. Uniform width peaks and amplitude the same, and not triangular. Part B, part 1. For an interference pattern to be observed, the light has to be emitted by two coherent sources. Explain what is meant by coherent sources. So these are constant phase relationship waves, or constant phase difference. You can say fixed phase relationship. They will be the same frequency and wavelength, but the mark is for saying constant phase relationship. Part 2. Explain how the use of the single slit in the arrangement above makes the light from two slits sufficiently coherent for fringes to be observed. So the single slit acts as a point source, spreading light to both slits, or the path difference from single to each of the double slits is the same. Alright, in this experiment, light behaves as a wave. Explain how bright fringes are formed. So, at the points on the screen where the path difference equals whole numbers of wavelengths, constructive interference or constructive superposition causes the bright fringes. Waves arriving at the point of a bright fringe are in phase, or their peaks overlap. So you can see what the three marks are given for. Path difference is whole number of wavelengths, 1 mark. Constructive interference or constructive superposition, 1 mark. And waves arriving at the point of a bright fringe are in phase, third mark, or you could say peaks overlap. See part 1. So a scientist carries out the Young's double slit experiment using a laser that emits violet light of wavelength 405 nanometers. The separation of the slits is 5.00 times 10 to the minus 5 meters. Using a meter ruler, the scientist measures the separation of the two adjacent bright fringes in the central region of the pattern to be 4 millimeters. Calculate the distance between the double slits and the screen. So there is a relationship here which we can use, which is the wavelength divided by the slit separation d is equal to the fringe spacing x divided by L, or big D. L is the distance between the slit and the screen. And so rearranging that to get L, which is the distance between the slits and the screen, is equal to xd over lambda. So fringe separation times fringe spacing times slit separation divided by wavelength. And we are given this information. So the x is 4 times 10 to the minus 3, 4 millimeters, times 5 times 10 to the minus 5, which is the slit separation, and divide that by 4.05 times 10 to the minus 7, which is our 405 nanometers, and that gives 0.4938 meters, or 0.494 meters to 3 significant figures. See part 2. Describe the change to the pattern seen on the screen when the violet laser is replaced by a green laser. Assume the brightness of the central maximum is the same for both lasers. So green has a longer wavelength. If we look at the expression that we can use generally for diffraction, d sine theta equals n lambda. So if we've got a longer wavelength, we've got green light, wavelength increases, so that increases the value of n lambda, and that therefore we must increase the value of sine theta because d is constant. So if sine theta increases, then theta must also increase. So the bright fringes get further apart. The angle theta is increasing. Part 3. So the scientists used the same apparatus to measure the wavelength of visible electromagnetic radiation emitted by another laser. Describe how he should change the way the apparatus is arranged and used in order to obtain accurate value for the wavelength. So you'd measure the distance from the slits to the screen accurately. We'll use a millimetre ruler to do that. You'd make this distance longer, e.g. 1 metre plus. That's because that's partly because there's a small angle approximation that we use in the equation, and that's only really valid when big D is very much greater than small d. So this distance between the slits and the screen is very much larger than the slit separation of the diffraction grating. We'd measure across several maxima, so this is where you're measuring the distance, the fringe spacing. Both of these would reduce the percentage uncertainty in the measurements. So by making the thing that you're measuring longer, you actually reduce the percentage uncertainty in that measurement. So there's 3 possible marks there. That should say 3 marks, not 4 marks. On to question 8. The student has a diffraction grating that is marked 3.5 times 10 to the 3 lines per metre. Calculate the percentage uncertainty in the number of lines per metre suggested by this marking. So we've got 3.5, so that suggests an uncertainty of 0.1, or we could say that we would round it to the nearest 0.1, so therefore the uncertainty is 0.05. If you go for plus or minus 0.05 divided by 3.5 times 100, it equals 1.4%, or you can go for an uncertainty of plus or minus 0.1, which is essentially the resolution that we've got this stated to, plus or minus 0.1. Divide that by 3.5 times 100 equals 2.8 or 2.9% to 2 significant figures. Either of those values would be accepted. 8b, determine the grating spacing. So we're given lines per millimetre in the question. What we want is millimetre per line, so it's 1 over d. So 3.5 times 10 to the 3 equals 1 over d. So d equals 1 over 3.5 times 10 to the 3, which equals 2.857 times 10 to the minus 4 metres per line, or 0.2857 millimetres per line. 0.29 millimetres to 2 sig fig is the answer. C. State the absolute uncertainty of the value of the spacing. So it's an uncertainty in this final digit, 9, of plus or minus 0.01 millimetres. Part D. The student sets up the apparatus as shown in figure 1 in an experiment to confirm the value marked on the diffraction grating. We have a laser wavelength of 628 nanometers, and we're given an interference pattern and a ruler to show us the scale. So use figure 2 to determine the spacing between 2 adjacent maxima in interference pattern. Show all your working clearly. So in this question, you've got to measure more than 1 spacing to get a more accurate result. So if 10 spaces are measured, then we would have a measurement of 5.24. Divide that by 10, gives us 5.24 millimeters. So sorry, 52.4 millimeters divided by 10 to get 1 space, 5.24 millimeters. Or you could use 25 spaces, which is 13.5 centimeters, and that would give you a value for 1 space as well. So answers in the range of 5.19 to 5.29 are accepted. So plus or minus 0.05 on that value. Calculate the number of lines per millimetre on the grating. So two possible ways of doing that. One is to use 1 over d equals x over lambda L. Put the values in, we get 3338 or 3400. Or you can use d sine theta equals n lambda, which gives lambda over d equals x over L. X over L gives us the two sides of the triangle instead of sine theta, and then rearrange that to get 1 over d, as shown here. F, state and explain whether the value for the number of lines per metre obtained in part E is in agreement with the value stated on the grating. So 3.4 times 10 to the 3 was the value we got, is within the range of uncertainty of 3.5 plus or minus 0.1 times 10 to the 3 lines per millimetre. And we have got a difference of 0.1, and as a percentage, 0.1 divided by 3.5 times 100 equals 2.9%. So 2.9% difference, so it is close. So 1 mark here for the saying it's within the range of uncertainty, and 1 mark for calculating a percentage difference of 2.9%. G, one safety precaution if you were to count that the experiment was carried out and performed by a student. So you'll know this if you've actually done this practical. You do not look directly into the laser beam, or you would display a laser warning sign, or you would take care to avoid reflections of the laser beam. Any one of those to get 1 mark. So question 9. The diagram below shows the paths of microwaves from 2 narrow slits acting as coherent sources through a vacuum to a detector. Explain what is meant by coherent sources. So that means we have a constant phase relationship, not in phase. The waves have a constant wavelength or frequency. So there is 2 marks for this question. B part 1. The frequency of the microwaves is 9.4 GHz. Calculate the wavelength of the waves. So wavelength equals speed of light divided by frequency. 3 times 10 to the power of 8 divided by 9.4 times 10 to the 9. Remember it's giga, which is 10 to the 9. That gives us an answer of 0.0319 or 0.032 meters to 2 sig fig. 0.03 would be accepted, as would 3.2 times 10 to the minus 2. So that's just writing the answer in standard form. Part 2. Using the diagram above and your answer to B part 1, calculate the path difference between the 2 waves. So we've got 6. One of them has a path of 6 wavelengths. Just counting the total number of waves, 1, 2, 3, 4, 5, 6. And the other one has a path of 5 wavelengths. So it's 1, 2, 3, 4, 5 wavelengths. So the path difference between the 2 waves arriving at the detector is 6 take away 5, which is 1 wavelength. Okay, so that's therefore a path difference of 0.032 because it's 1 wavelength. You would be allowed an error carry forward here. Your value for the path difference should be the same as your value for the wavelength that you calculated in the previous part. C. State and explain whether a maximum or a minimum is detected at the position shown in the diagram. It would be a maximum. This is where the waves arrive in phase. The waves meet in step. There's constructive superposition taking place, and the path difference equals a whole number of wavelengths. So there's 3 marks available there for possible statements you could make. Part D. The experiment is now rearranged so that the perpendicular distance from the slits to the detector is 0.42 meters. The interference fringe spacing changes to 0.11 meters. Calculate the slit separation, give your answer to an appropriate number of significant figures. So we're going to use the relationship lambda over d equals x over L. Lambda is the wavelength, which we've calculated previously. D is the slit separation. X equals the spacing between the fringes, and L equals the distance between the slits and the screen, or the detector. So rearrange that to get D. D equals lambda L over X. Put the values in. 0.032 times 0.40 divided by 0.11 equals 0.122. So the slit separation is 0.12 to two significant figures. The third mark here is for any two significant figure number. Any number to two significant figures will get you a third mark. Just being really careful here where it says to give your answer to an appropriate number of significant figures. The values given in the question are both to two significant figures, so you can't state an answer to more than two significant figures. Part E. With the detector at position of a maximum, the frequency of the wavelength of the microwaves is now doubled. State and explain what will now be detected by the detector in the same position. So a maximum will be detected. So we're a bright fringe, which is a maximum microwave, and that's because the wavelength is halved. We've doubled the frequency, and the potential the path difference is now equal to two wavelengths instead of one, but it's still equal to a whole number of wavelengths. So maximum is detected. So maximum detected, 1 mark. Wavelength is halved, 1 mark. Path difference is a whole number of wavelengths for the third mark. So well done if you've followed all of that. So we've now got to the end of the waves questions. If you've got the workbook, then you can have a look at the mark scheme, which gives you essentially what I've explained to you, just as the examiner would give it. It may be helpful for a quick reference to have a look at the mark scheme, or you can just rewind the video and go back to any question that you need to spend a bit more time on. So thank you for your participation. I hope that was helpful. Do look at the other videos which are on the other topics covered by the A-Level Physics Year 1 workbook. Thank you very much. Bye for now.